Welcome back to Physics 246 Online. Today I'm going to give an overview of the first three sections of Chapter 7 in Bevington and Robinson's book, which is really the bulk of Chapter 7. It will parallel our discussion from the chapter on the method of maximum likelihood used to perform a best fit to a linear function, except now we're extending this to a more general polynomial function that has a larger number of terms. This is going to be fairly dense at some points. I'm not going to work through every single step that's outlined here in this presentation. You can refer to the textbook for more details, but this should help you as you read the textbook and try to understand the basic concepts from Chapter 7. So consider that we have some kind of sample population, and to give a specific example, this might be voltage versus temperature measurements that are taken using a device like a thermocouple that reads out a voltage depending on the temperature of the surrounding environment. And we would like to know what the best fit polynomial function would be that would relate that voltage to the temperature. And in general, we would be interested in some general function, y as a function of x. We assume that the specific data points that we are able to measure come from an infinite parent population that's characterized, in this case, by a polynomial relationship. We also assume that we can use the finite sample population that we've measured to determine the most probable population from which those data came. And finally, we will assume that that most likely parent population approximates the true parent population that the data surely came from. In other words, the parameters, the fitting parameters, A1, A2, A3, and so on, will approach, as we have a large number of data points, they will approach the parameters that characterize the true parent population. And again, we're using the method of maximum likelihood, in which we write down the probability of obtaining the specific sample population that we did obtain from the parent population. So the probability of getting in our sample population a particular measurement, which is just one set of data, xi, yi, characterized by a sigma I, is this familiar Gaussian form that we've used before. And the general function now we're going to express in summation notation because it's a polynomial function characterized by a coefficient and then a power of x. So these parameters all appear, the data points all appear in this probability function. And now we want to generalize our functional form for the parent distribution function, or for the fitting function itself, which normally would be a polynomial function of powers of x, but in general it could be something else. It could be a linear combination instead of powers of x. It might be a linear combination of powers of the cosine of an angle or some other type of function. And so rather than just use x here, we're going to replace that with f sub k, which could be some general function. And so if these f sub k's were to represent a power series, the traditional polynomial function that we're familiar with, then the first f expression would simply be 1 because that would represent the constant a1, and then f2 would be x, f3 would be x squared, and so on and so forth, including as many n terms as we thought were valid to use in a polynomial fit to our data set. But in general, like I mentioned earlier, these f sub k's could represent other kinds of functions of x. It could be a cosine function, or it could even be a function of the cosine function. And so this kind of approach can be used for a series of functions that may be the traditional x, x squared, x cubed, but they could be more general kinds of functions as well. The same method would hold true. So at each data point, of course, we've measured y and its uncertainty, and then y of x sub I is the value of y at x sub I that's expected from the parent population. and we're going to substitute in our fitting function result for that term. So we wrote down what the probability is of getting a single data point from the parent population, but now, assuming that we have n data points that we've actually measured, the probability of getting that entire set would be the product of all of the individual probabilities. And again, you've seen this before in the context of our linear fitting function. So what we now have to do with this term here is we generally describe or define this summand as the chi-square value associated with data point I. And then the total chi-square value is the sum of all of those individual chi-square values. So remember, the logic behind the method of maximum likelihood is that in order to maximize the probability that our data set came from a particular parent function, we're going to try to minimize the chi-square value because it appears as the negative term in this exponential function. So to maximize that, we will minimize the exponent, which means minimize the chi-square value. All right, so far this should be fairly familiar if you remember what we did earlier. So we want to minimize the total chi-square, which means we want to minimize the sum of the squared deviations, and this is sometimes called the method of least squares for this reason. The method of maximum likelihood and the method of least squares are just two different ways of referring to the same method. So in Chapter 6, we minimize the chi-square for a linear fitting function with respect to the two parameters of a linear function, the slope and the intercept. However, now in Chapter 7, we want to do this same approach, carry out this same approach for a function with a larger number of parameters. Small n is the number that we use for that number of parameters, so we'll have to take derivatives of chi-square with respect to each of these parameters, and this will lead to a series of n independent linear equations. And each of those equations will contain one of the n parameters. And by solving this system of equations simultaneously, we will be able to determine the values of those n parameters that we seek. And those parameters represent the constant terms that are in our polynomial fitting function. So the basic approach of taking the derivative of chi-square with respect to each of the parameters and setting that equal to 0 will give us the n equations that are summarized in the textbook in equations 7.6, 7.7, and 7.8. So here we'll just take a quick look at 7.6. This is the derivative taken for a general parameter a sub L. So we take the derivative of chi-square, and that derivative is fairly easy to work out. And finally, just taking this expression here, setting it equal to 0, and doing a little bit of rearrangement, we get equation 7.7, the last line here on my slide. And you'll see that it depends on things like the individual functions, f sub L, which for a simple polynomial would be x, x squared, x cubed, and so on. It depends on the data points, y sub I, the errors in those data points, sigma sub I, and we, of course, have to sum each side of this equation over all of the capital N data points that we've actually collected. So let's just rewrite that equation and show what it might be for some specific cases. So if we just look at L equals 1, then we would see that these f sub L's become f sub 1's. So f sub L becomes f sub 1, f sub k becomes f sub 2, and so on. So we have on both sides of this equation this sum over the total number of data points, and this is specifically what the first equation would look like for the first term in our fitting function. And usually in a standard polynomial function, that f1 would simply be the number 1 because it would represent the first term, which would be the constant term. So that The first line here shows again that L equals 1 term. The L equals 2 term has the F2 on the left-hand side, and then the F2 on the right-hand side in place of the F1. And then the 3 term would have F3 on both sides. So once again, you'll have, depending on however many parameters there are in your polynomial function, you'll have that number of equations. And those equations are independent of one another, but you'll notice, look at the first equation. It contains not only the A1 that we're trying to solve for, but it contains all of the other A's as well, A2, A3, A4. So we can't just solve the first equation to get A1, we have to solve these equations simultaneously. And the best way to do that is through the method of linear algebra. So we can take these equations and pull out from each of those equations. Again, I've just rewritten the L equals 1, 2, and 3 equations, but in each for each term on the right-hand side, I've pulled out the parameters A1 from the summation, and then A2 from the summation, and of course you would have however many terms here as you would have parameters in the fitting function. And the second and the third equations look the same. So now we can really see that these A1, A2, A3 terms represent a set of constants that could appear if we rewrote this whole series of equations in matrix form. So you've got these summations in the terms on the right-hand side, each of which can be calculated directly from a knowledge of the x sub I data points and the functional values at those x sub i's, as well as the uncertainties sigma sub I. And those would represent the coefficients in the matrix on the right-hand side. And of course, the terms on the left-hand side would also be easy to calculate based on the measured y values. So we would solve for the parameters A1, A2, A3, and so on using the method of determinants as we did in Chapter 6. And the results, if we had 3 terms, which could be the case for a simple second-order polynomial, where we'd have the first term of a constant, A1, the second term would be A2 times x, and the third term would be A3 times x squared. For that simple kind of polynomial function, using the method of determinants, we would define this quantity delta, which just looks a little bit more complicated than the one we saw back in Chapter 6. It's the determinant of a 3×3 matrix. And then the A1 term would be 1 over that delta multiplied by the determinant of another set of 3×3 equations. And the A2 and the A3 similarly. Okay, so I don't want to work through each of those in detail. You can take a look at the textbook, but the method is all quite straightforward once you express the series of equations in matrix form. So to carry out that kind of a solution on a spreadsheet, you would form columns of the values needed. Of course, the first simple columns would be the data points themselves, the independent and dependent variables, the error in the dependent variable, and then these terms would all represent the value of that particular term in the fitting function for the data point x sub I. And then finally, in order to determine the quantities that are on the left-hand side of our equation, we'd have the product of y sub I times those individual f values. So these form columns of quotients or products of the weights. We would sum the columns, substitute into the equations to get the values of a sub k. But of course, you can see that doing this for a 3×3 set of equations or a 3×3 matrix might be okay, but doing it for anything much larger is really going to be quite tedious. So more conveniently, the way you're going to do this is to use a matrix method for solution, and spreadsheets like Excel are set up to do this quite nicely. So once again, equation 7.7, we can go back and write it this way. We'd written it out equation by equation before, but if we just go back in a simple form here, then we can identify the term on the left-hand side of this equation as the elements of a matrix that we'll call the beta matrix, where the kth element of the beta matrix would be the term here. And then on the right-hand side, we'll define the term that multiplies each one of the parameters, each one of the A sub L parameters, we'll refer to this as the alpha matrix, where, of course, the beta matrix is just a one-dimensional matrix. It's got, if we have 3 terms in the fitting function, it's got 3 terms in it. The alpha matrix is a square matrix, and so it's got indices L and K that are determined by the products of the individual terms that are in the fitting function. So in matrix form, we can write this as a matrix beta is equal to a matrix alpha for the coefficients multiplied by the matrix, what I meant was beta matrix is determined by the A matrix for the coefficients multiplied by the square matrix alpha that comes from this term here. So in short, we would write this in matrix form as beta equals A times alpha, realizing, of course, that let's say that we had 3 terms in our fitting function, then beta would be a 1 by 3 matrix, A would be a 1 by 3 matrix, and alpha would be a 3 by 3 matrix. So it would appear in this form, right? These 3 terms, beta 1, beta 2, beta 3, would be given by the matrix multiplication that you would get from the matrix A1, A2, A3 multiplied by the square matrix, the alpha matrix. So in the familiar rules of multiplication of matrices, the A1 would multiply the alpha 1, 1, the A2, the alpha 2, 1, the A3, the alpha 3, 1, and that would give you, the sum of those products would give you the first term on the right-hand side, which would be the beta 1 term. So you've probably done this in a math class before, but even if you haven't, Excel allows you to do these kinds of matrix multiplications quite easily as long as you know the elements of each of these matrices. So again, in matrix form, what I just read out was the first line here that tells us how the beta 1 term would be generated by taking the product of these two matrices here. And a similar kind of equation would give us the relationship for beta 2 and for beta 3. So here is the clever thing, and this is what a program like Excel does very nicely, especially if we have large matrices, a large number of terms in our fitting parameter. So we rewrite this matrix equation as beta equals A times alpha. Then we multiply the right-hand side of each side of the equation by the inverse matrix alpha inverse. And there's a procedure for determining the inverse matrix. But the property of the inverse matrix, and the reason that this is a useful technique, is that any matrix alpha multiplied by the inverse matrix just gives you the identity matrix, which it has 1s on the diagonals and 0s everywhere else. So alpha times alpha minus alpha to the minus 1 power, or the inverse of alpha, is equal to the identity matrix. So doing this procedure to our original equation leaves us with a really nice result that the A terms are just given by beta times the inverse of alpha. And to make the notation a little bit more convenient, we're going to redefine the inverse of the alpha matrix as the epsilon matrix. And we'll give that a name in just a minute. So the values of A themselves, if we can form this inverse matrix of alpha, the values of A are just given from beta times this inverse matrix using the familiar rules of matrix multiplication. And that's what the spreadsheet is really good for. Now a question, once we've determined each of these parameters that are in our fitting function, we want to know whether they're independent of one another. And in general, they're not. It actually would be quite unusual if they were independent, but let me just explain what I mean by this. Let's say that we had 4 terms in our fitting function, and we determined the fit using those 4 terms. We got A1, A2, A3, and A4. So let's imagine now that we fit the same data set, and we just imagine that we added one more term. So instead of maybe having a term that went up to x cubed, we now include a term that would go to x to the 4th power. And that would allow us to refit the data using this larger fitting function and get a completely new set of A1, A2, A3, A4, A5 that we'll indicate with primes here. So if the individual terms in the fitting function are independent of one another, then we would expect, for example, that the A1 prime term would be about the same as the A1 term. and so on and so forth. The only additional thing that would happen is we would have the A5 prime term. However, in general, this is not the case, because most of the time, when you change the number of terms in your fitting function, the results that you get for each of the parameters, each of the coefficients, tends to be altered by the presence of the additional term in the fitting function. So in practice, that's not what happens. And if these individual parameters are not independent of one another, then what do? How do we determine which fitting function is best for a particular data set? And we will show, as we get into Chapter 11 in a week or two, we will show how you can use the chi-square test to test a series of fits with different numbers of coefficients and figure out which one provides the best fit. So more on this in a week or two. But for now, let's imagine that we've carried out this rather complicated fitting function for a polynomial. We've carried out this procedure for a polynomial fitting function, and we want to know for a particular x value, when we calculate the y value based on these fitted coefficients, a1, a2, a3, so on, what's the error going to be in the y value that we calculate at a particular x value based on our fitting function? And it's not too difficult. We've done things like this before. We'll go back to equation 313 as our guide and set up the expression for the variance in y. Now, in general, this variance is going to contain in it expressions involving the variances in the individual coefficients, and in general, it could include the covariances in those a sub k values. So you'll have coordinated variances, the way that the a values for the jth term affect the a values for the kth term. And although in previous assignments we have often assumed that these covariance terms are either small or zero, in this case it's not going to be safe to make that assumption. So the terms that appear in our variance of y are going to have individual terms in it that have derivatives of y with respect to the individual fitting parameters. So going back to equation 313, which you've seen before, right? Sigma y squared is going to contain the different terms that appear in equation 313, and there'll be a series of them that will be the variance terms. They'll be the ones that have in them the variance in each of the individual fit parameters times the derivative of y with respect to that fit parameter squared. So those will be the variance terms, but then they'll also be the covariance terms. And we won't be able in general to assume that those are small. So to get those values, what do? Well, we get them from the individual uncertainties in the data values themselves, right? So this term here for the variance in the kth coefficient in our fitting function will be given by this expression here. And then the covariance term for the jk combination of fit parameters will be given by an expression like this, with these derivatives in them. And so what we will need to do is determine what the derivatives are of each of the fit parameters with respect to the measured y values. So to calculate those derivatives, we just go back to the expressions that we got for the values of a sub l from our matrix solution. And here, for example, is what we had. It's an equation 720 in the textbook for a sub l. It was the sum that included the epsilon terms in that inverse matrix multiplied by this quantity here. And we just take that expression, differentiate it with respect to the yi terms. When we do the math, we get this expression here, dal by dyi. That will get substituted into the various locations where we need it in the expression for the variance in the fit parameter, ak, and then the covariance term as well. And here, we'll just use a little bit of color coding with these bars to show what's going to happen when we calculate the covariance term. Okay, the sigma I term gets carried over. The derivative of aj with respect to yi would be here. A similar term for the derivative of al with respect to yi. And then we can rearrange this expression just a little bit to pull out those epsilons from their individual fits. And finally, what we get, and I'm just going to show you the equations, but then refer you to the textbook for more details. What we get when we determine these covariances finally amounts to simply the elements of the inverse matrix. And remember, epsilon was the symbol that we used for the alpha inverse matrix. It's a square matrix, so it's got a jk term, and the jl, I believe maybe this should be JL here at the end, right? It should be JL because it's the JLth term of that matrix, and it represents the covariance between the AJ and the AL terms in the fit function. So definitely that's what that should be. Oh, by the way, this 1LK term, that looks a little bit odd, but 1 here is the notation that we're using for the identity matrix. So the punchline here is that this epsilon matrix, which we're now going to call the error matrix, we've already determined it used in the solution of the individual fit parameters themselves. And the really nice thing is that the elements of that epsilon matrix also give us the covariance terms that we want. And so we're going to call that epsilon matrix the error matrix, and it's a square matrix again. The interpretation of it is that the diagonal terms, for example, the 1, 1 term, the 2, 2 terms, those are sigma squared A1, A1, which simply represents the variance of the A1 term, and so on and so forth. So if we have those values of epsilon 1, 1 and 2, 2, those themselves, if we take the square roots, will give us the error in that particular fit parameter, A1 or A2. The off-diagonal terms in that matrix, the epsilon 1, 2s or the epsilon 3, 4s, those give us the covariance terms that we need in order to calculate the variance in our value y for a particular value of x. So we're almost done. Going back then, that sigma y squared, according to equation 313, right, we have the sum of all of these terms that have the variances, and then the sum of all the terms that have the covariances. And now this simplifies using the error matrix into the form like this, where again the diagonal terms in the error matrix give us these individual A1, A2, A3 terms. The off-diagonal terms give us the covariance terms. And just to finally remind you that this doesn't even involve an extra step in the whole solution process, because we had to compute these epsilon matrices anyway when we were solving for the a sub k's. So the homework assignment is going to give you some practice carrying out a simple polynomial fit using first XL to set up a matrix technique for doing the calculation, and then we'll use our Igor Pro program to do the same kind of calculation a little bit more easily, because Igor Pro does more of the steps for us, and we'll be able to compare the results and make sure that the Igor Pro result is doing things the right way. Well, thanks for wading through this. I hope it helps as a companion to the textbook as you read Chapter 7, and I'll see you in class.